So my name is Mathis, and I'm going to present my PhD work entitled Natural Language Control for 3D Human Motion Synthesis. So to start with, let's look at this shot for the movie Spider-Man No Way Home. So as you can see, it involves a lot of very complex human motions, and so we can wonder how did they create such a sequence. So they rely first on motion capture. So there is real actors which are doing stunts in the scene like that, but they use some special suit, motion capture suit, which can be composed in this example with dark and gray triangles. Then the actor can do the stunts, and then the motion can be recorded in 3D. There is it's also possible to use indoor motion capture studio like this one, so the actor can do the motions, and it can be then retargeted to this Spider-Man character. For some very complex scenes like this one, actually the whole environment is modeled in 3D, even the cars and the human motions, like this on two characters. And for some specific scene, the animators will animate the motion frame by frame, which is very tedious. So actually the whole process is very long, very costly, and it's very tedious. So this is about movie for human characters, but also for non-human characters, such as apes. We can do similar process. From human motion capture, we can texture them to get this final shot. Human motions are also crucial for video games because it needs to have immersive experience. So in Assassin's Creed, to have some beautiful jumps like that, it also relies on motion capture with humans doing their motions. For augmented reality and virtual reality, we are also very interested to have nice human motions to display the character in a video game. And so for this, in the MetaQuest, actually the legs are generated. There are no sensors with the legs. So let's talk about some potential application of language control for motions. So first, we can think in the future of a virtual fitness coach. So an application could scan the body, then propose some exercise, and then we can have a virtual character which can guide you how to do a certain motion. And then the virtual character can also tell you what to correct, for example, the posture. Also, if we think of text to, if you have a model which do text to robot motion, we could think of giving commands to a robot, and then the robot could do some actions like cleaning the dishes. So this video is from OpenAI. So the main hypothesis of this PhD is, what if we can generate human motions by a computer and to control the generation with natural language, such as English or French? So this hypothesis has already been successful with images. So we have some text-to-image models, which take a prompt like this: a family eating sandwiches in the forest on a sunny day on a red and white tablecloth. And then DALL-E, for example, can generate such nice image. So we want to do the same for human motions. So given a text which describes some actions, person is walking forward, raise both arms in the air and jump, then we want to have a model which generates such motion. So this is from a work I made. So why generating motions? So first, it can save production costs. So it can be way faster and simpler. And also, we can think of something else. If the computer, if we teach a computer to generate motion given a text, it means that the computer learns the association between the text and the motion, so that the computer understands the complex language of human motion. So why is it a hard problem? So first, human motions are very complex. It's a high-dimensional problem. It involves a lot of body parts, and we need to generate the trajectory over time. Also, natural language is ambiguous, so we can have several texts which correspond to one motion, and also several motion could correspond to a single text, so there is not a one-to-one correspondence. Also, temporal modeling is an open problem. It's actually quite hard. If we have some RNN models, it can produce a jitter motion, like this one. So in this PhD, I use like a transformer architecture, so that the output motion is more smooth. Then the diversity. So the generation needs of the model need to be diverse. We need to capture different modes. For example, with an action such as throwing a ball, it can be done with the left hand or the right hand, and the other body parts can be something else, but we need to have different way of doing the motion. Then in this area, we have the training data is not large scale, so this can be also a big issue. And finally, as in other domain, evaluating generative model, it's a challenge. And so it's hard to assess the quality of motion generation. That's why we often use human studies instead. So here are the tasks I addressed during my PhD. So first, the five first tasks are motion synthesis. So first one is action. So given an action category as input, such as pickup, to generate a human motion. Then we go with free-form text condition synthesis. So we have a human walking in a circle clockwise, so it's a full sentence. Then as input, a sequence of text, such as hold golf club while looking at the ground, swing golf club, jog forward and kneel down. So it does all these actions one at a time. Then spatial compositionality, when we have simultaneous actions to do at the same time. For example, put hands on the wrist and move torso right. And finally, I work on this multi-track timeline control for motion synthesis, where it generalizes both the spatial and temporal compositions. So you have a timeline in the input, and you need to have a motion which corresponds to all of this in time. So we have walk forward, then rising both hands in the air, and then jump. And all these motions should be generated like this timeline. Finally, I also work on text-to-motion retrieval, which is given a text prompt and a gallery of motion. We need to sort the database by similarity with the text. For example, human walks up the stairs, and we'll retrieve some motion in a database which correspond to the text. So we'll give more detail about this later. So all this project led to several publications, to various conferences. And in this presentation, I will present Actor, Theos, and TMR specifically. So let's look at some background first. How to represent a 3D human motion. So there is different way. I think the most straightforward is to record the XYZ location of all the body parts corresponding to some skeleton representation. So there is different skeleton representation available. Then there is also, we can also use parametric body models. In early day, we use parallelepipeds or cylinders or elliptical cylinders. But nowadays, we are more interested into model the skin of the body, so the output skin. So simple disentangle the body shape variation and the pose variation. And then you have also some following work which also models the face and the hands and have more and can generalize to more diverse body shapes. Let's discuss a bit about the literature of 3D human motion generation. So in early days, most methods generate only some walking or running motions with statistical models. Then some work focused on character control, mostly in computer graphics or in video games, when you have some joystick control and you need to generate a motion which follows the trajectory. But also there was some work which use some text as input, such as a girl is playing drum, and so this work text to action models the upper body of the motion. Then you can have some audio as input, or some music. So this dancing to music, there is some music, and then this character is dancing. And then there is some work with action to motion. From an action category, generate a motion. So that was before my PhD. Then in 2017, the transformer model came up, and it has a huge success in natural language processing and in also later in vision. So when I released this actor project in 2021, then I used transformer. So I'm one of the first model to use transformer for motion generation. And then later on, a lot of projects use also transformers. So motion diffusion model, MDM, to have this generation also use transformer as a backbone for the denoising process. Then MLD, motion latent diffusion, use the actor embedding space to generate to do the latent diffusion. And finally, this this state of the art, very recent MoMask, use also a transformer architecture for the motion generation. So let's dig into actor. So actor is an action condition generation model. So it takes an action category as input and generate a motion which corresponds to the action category. So the first question is how to obtain training data. So actually there is a lot of action recognition data sets available where there is videos of people doing a certain action, for example this flow. So we use some state-of-the-art motion estimation methods, so at that time it was VAE, to estimate the motion given the video. So this is the output we get, the estimation. And then from this estimation, we have the action label. And so we create a motion action pair. And by doing so, we can create a data set of motion and text and action category, sorry. So we did that for several data sets. So NTU contained 13 actions, USTC 40 actions, and Humanec 12 actions. And so we can train a model. So we'll discuss about it more in detail. So actor, so action condition transformer VAE. So how does it work? It takes a random vector Z, which can be sampled from a Gaussian distribution of mean 0 and sigma equal to density, so a unit Gaussian distribution. An action category A, such as pickup, the last example, and the duration T, and it generates human motion corresponding to the input. So this is a generator part, but as I told you, is a variational autoencoder. So the generator part is at test time, but it's actually the decoder at training time. And if it has a decoder, and so I will explain you what is the encoder. So the encoder takes as input an action category, the motion, and it produces Gaussian distribution, which corresponds to the input. So it's kind of summarizing the information of the motion. And from this distribution, we can sample the latent vector. So that's the overall idea of the architecture. To give you more specifics, so the action category A, from it we learn learnable tokens, mu A token and sigma A token, like in BERT or in a vision transformer. The motion are embedded into an embedding space, and then we add positional encodings before feeding that to a transformer encoder. Then we can get the first input to get the mu and sigma output. And for the decoder, for each action, we learn a bias token, from which we add to the latent vector Z. Then the duration T is used to know how many positional embeddings we will put as input to the transformer decoder. and then we just linearly project the output to get the motion back. So the decoder is a transformer decoder, but it's not autoregressive. It's non-autoregressive because we are doing only one forward pass to get the motion. To train this model, we use, because it's a variational encoder, we use KL loss, KL divergence loss, between the distribution and the unit Gaussian distribution. And then for the reconstruction losses, there is one loss to constrain the motions, the rotations of the motion to be the same, but we also constrain the vertex to be the same by inputting the rotation through the simple differentiable simple layer to get the vertex. And so we add these three laws together. Let's look at some qualitative results of actor. So here you can see the motion and the corresponding input on the bottom. As you can see, the motions are quite smooth and correspond to the action categories. Here are some other examples. Let's compare actor with prior work action to motion. So that was the generation of action to motion. So it's a frame-by-frame variational autoencoder. And as you can see, it's very jittery. Also, it generates only the joint positions, whereas in our case, we are generating the simple post parameter. And that's the difference with our method. So to evaluate quantitatively the difference between actor and action to motion, so we can use a pre-trained action recognition network, which take a motion as input and classify the action. And we can compute the action recognition accuracy. And as you can see, actor is closer to the real motion in comparison to action to motion. We can also compute the FID, the featured inception distance. With the same action recognition network, we can extract latent features, latent motion features from the last layer of the network. And from these features, we can compute statistics, mu and sigma of the distribution of the ground truth and the distribution of the generated motions. And by doing so here lower is better, so the actor is way closer to the real motion than the prior work of action to motion. So actor can produce diverse output. So with the same action, we can have a different latent vector. And if we sample with differently, we can have different motions. So with standing toe touches, you can see it can be done one time or twice, or with different starting point and different styles. With the action sidekick, it can be done with the right and the left leg, but also the placement of hands can be different. Actor is so it's a variational encoder. So it comprises of an encoder and a decoder. As you remember, the real motions are very jittery because it's from monocular estimations. As you can see on the left, it's very jittery. So I don't know in Zoom if you will see this, because sometimes we don't see it jitter too much on Zoom, but it's jittery. But if we take this real motion, we encode it back to actor and decode it back, this is what you get on the right. The motion is way smoother. Same thing with arm cycling. As you can see, it's jittery on the left, but then if we encode and decode the same motion, it's become smoother. So there is one thing we can look at in the latent space. From the same action, we can sample different vectors. And if we interpolate in the latent space from one vector to another, we can have some emerging property. For example, with the action throw, it can be from a low hand to a high hand. As you can see here, the hand is larger, it's upper in the air comparing to the one on the left. So actor has some failure cases because we only generate positions. There is no loss to constrain. There is no loss to prevent collision. So you can have some mesh interpenetration with the hands or with the legs, for example. Also, some motions are very fine-grained, such as head anti-clockwise circling, as you can see on the left. But it seems to be very jittery. So actually, the model, because it generates smooth output, it actually didn't perform this action. It's a freezing motion. So to conclude, Actor is a sequence level. It uses a sequence level motion embedding. It's not an autoregressive. It's not autoregressive, and it generates realistic and smooth outputs. We show that with noisy motion estimates, we can provide training for action condition synthesis, and we can have this denoising as a side product. And finally, we use parametric body models, and we put reconstruction loss on rotation and vertices. So here in Actor, we use a fixed set of action categories, such as this. But what could be nice if we can input free-form text, such as this example. It will be a better way to interact with the computer. So that's what I'm going to present right now with Theos, text condition synthesis. So in this project, given a textual description, in English, a human walking in a circle clockwise, we want to generate multiple motion sequences which correspond to the text, such as these three below. As you can see, all three correspond to the text, but they follow different trajectories. We want to generate skeletons, but as in Actor, we also want to generate simple post parameters, such that we can generate these bodies. Some prior work at this time of this paper, so there is this language to pose and Ghosh et al. They both are deterministic. That means they can only produce one motion given a text, and they both use an autoregressive decoder. So in this work, we use also a probabilistic model, and with a non-autoregressive decoder. So for this project, we use motion capture dataset. So there is this dataset called KIT Whole Body Human Motion Database, which we call body indoor, and map them to some robot body. Then KIT Motion Language Dataset annotated these motions with text, so that we can launch a model with this robot motion, MMM motion, with the text. And then some years later, there is this AMAS dataset which came, which took a lot of different motion capture datasets and merged them together and unified them with the same parametrization by using the simple body model. So in this work, I made the mapping between the motions of KIT motion language. Instead of taking them from the robot shape, I can take directly from the AMAS. So in this way, we can generate from a text with this robotic skeleton, with also the simple skeleton, which is, in my opinion, more realistic, and also with the simple post parameters, so that we can get the shapes like that, the vertex. Let's look at Theos, the architecture, more in detail. So given a text, such as walking in circles, so it's a sequence of words, we can use pre-trained language model, which is frozen, such as Distilbert. From this model, we can extract text features. And then, similarly to Actor, we can use a transformer encoder with learnable parameters to get a Gaussian distribution which corresponds to the text. Then from this distribution, we can sample from it a latent vector Z text. And from this latent vector, we can decode it with to a motion. So the decoder is the same component as the Actor decoder. So this is the text to motion branch. That's how we use it at test time. But for training, we also use a motion encoder branch. As in prior work, it helps to structure the latent space. So actually here in blue, it's a switch. We can go from the left side to the upper side, or from the bottom to the up on the right. So we can go either left or right. So it's a motion branch or text branch. So Theos, in contrast to prior work, it generates multiple motions per text, and it can generate skeletons or simple bodies. Also, it's really a generation from scratch. The first frame is not needed, and it uses a non-autoregressive architecture. So how to train Theos? Theos uses several losses. So it uses two reconstruction losses. One which go from the motion branch to the output, and then we try to reconstruct the motion we give as input, and then reconstruction loss on the text branch. So we will compare the generated motion from the text, and we will compare with the corresponding motion pair, like on the bottom right. Also, we use some KL diversion losses. We want both distribution to be similar to Gaussian unit Gaussian distributions, and also we want both Gaussian distribution to be similar one and the other. Also, we put a loss between the two embeddings, the motion and the text. We want them to be as close as possible. And finally, the total loss is a weighting sum of all these terms. So while some terms may appear redundant, we experimentally validate each term. Let's see some comparison with prior work. So with the text, a person walks 2 steps, turn around and walk another 2 steps. So that's what the ground truth looks like. And then let's see some prior work. So Lin et al. Actually doesn't really do the motion. So it's the first work to do text to motion. So that's maybe why. Joint language suppose is doing walking motions but doesn't turn around. Gauche et al. Actually follows the semantic. It does the action but lacks a bit the realism. And finally, Theos works better. Then look at another example. With the text description, a human performing a kick with the right foot. That's the ground truth. Then Lin et al. Again doesn't work. Joint language suppose actually works good. Gauche et al. Suffer from elongated limbs. That might be due to some extra losses on the foot contact or with the parametrization. And finally, Theos works good. So also to have some other metrics, we also did some human studies. We asked AMT users to respond to questions. So which motion corresponds better to the text and which motion is more realistic without showing them the text. So that's what it looks like. So we show the two motion and then user, in this case, it should click on the left. So here we show the performance. So the red line is equal preference, and when we are upper Theos is preferred. As you can see, even with Gauche et al., which is the state of the art, we got we are prefer more than Gauche, 70% of the time for semantic preference, and more than 90% of the time for realism. So among different metrics, we can look at the average position error on the root joint. So it's basically the average of the L2 distance over time frame and the test sample between the generated trajectory and the ground truth trajectory. And by computing this metric, we also show that Theos performs better than prior work. And here, Theos, because we can generate several samples given a single text, we can actually generate 10 of them and took the one which is closest to the ground truth. And by doing so, we show that we can further improve the metrics. So Theos produces diverse outputs. Given same text, same duration, person jumps forward, you can see that the jumping distances can differ. Also, with the text description, a person performs a squat. So here this constraint is a bit more limited in terms of the freedom, but as you can see, you saw the style was a bit different, and the timing. So Theos has some limitations. So first, it has a restricted vocabulary. So that's because of the ground truth data, which is not large scale. If we want to generate out of distribution text, such as a person plays a piano. In this example, it will play the violin. That's just because in the training data, the word play is associated with the violin, because there is playing the piano is not in the training set. And also, Theos it works mostly for single action. So if we ask for spatial composition when motion occur at the same time, it doesn't work super well. And also, same thing for temporal compositions. So that both aspect has been led to some to the Teach and Think project I presented briefly earlier. To conclude, Theos shares similar components with Actor. It can generate both 3D joints and simple post parameters. And in Theos, we learn a joint latent space between text and motion. And that's actually this last property, which we will use in the next project I will present, TMR. So TMR is a text-to-motion retrieval. So the goal is given text as input, such as someone is walking in a circle clockwise. We have a gallery of motion, which may not be annotated. And we need to rank the gallery by similarity with the text. So you can see to rank one, it corresponds to the text, but then it doesn't correspond anymore. So why text-to-motion retrieval? First, so text-motion retrieval, we will search among an existing collection of text, which can be interesting if you have a large collection. So it can be used instead of synthesis if it can be used also as initialization if you want to do another task. Also, the retrieve motions may be more realistic than synthesis because it's kind of ground truth. And also, we can use it to localize a motion in a long sequence. For example, here, we can be interested only in the backflip. And so we could make use of a text-to-motion retrieval to get this. So why not text-to-text retrieval? Mainly because the motion gallery could not have labels. And it's actually very costly to annotate a database when it's a large scale. So that's why we use text-to-motion instead. So that's another setup. So at the time of the paper, there is this work of Guo et al., which is actually a paper on motion generation. But in the paper, they also provide a model for doing text-to-motion with a margin loss. And they used this model as an evaluation metric for motion generation task. Also, we can think of text-to-image retrieval. So CLIP is well known in the field of vision. It uses image encoder and a text encoder and try to make them as similar as possible. So TMR, I will explain to you how to use it at test time. So it's a dual encoder, such as in Theos, and it also it has a cross-model embedding space. So given a text query, such as someone is walking in a circle clockwise, we will encode it with the text encoder into the embedding z-text. Then we'll take the whole database of human motions. We will encode all of the motion independently. And then we can compute cosine similarity between the text and each motion. And this gives a score. So with this score, we can sort the database in order. Also, this score can give also a way to evaluate how far a text and a motion are together. So how to train TMR? So it uses contrastive learning with N4 and CE. So it's the same loss as in CLIP, as it was very effective in CLIP. So basically, we encode all the text in a batch and all the motion. And then we will compute this similarity matrix. And basically, we want to maximize the diagonal and minimize the off-diagonal terms. TMR is trained jointly for retrieval and also for synthesis. So it's actually the same architecture as in Theos with additional losses. So why keeping the motion generation loss? Actually, if we have in a batch, for example, the text doing a left kick, we don't want the model to cheat, and we want the model to really understand what is a left kick. So by having the generation loss, the model is forced to learn that it's with the left leg, so it helps to structure the latent space. Also, in TMR, we use a filtering of negatives. So actually, in the ground truth data, in the motion domain, a lot of texts are very similar. For example, there is a lot of walking in a circle or derivative of this. If we keep all of them, we will put them as negatives, and it can deteriorate a bit the results. So here, when the text is very similar, when two texts are very similar, we consider them as wrong negatives. So we don't use them in the contrastive loss. To train TMR, so that was the dataset of Theos. But then there was some other dataset which came. So there is Babel dataset, which annotates also a subset of AMAS with text annotations for mostly short segments. And HumanML3D, which also provides some text annotations from AMAS. So we train TMR on HumanML3D, and then we can test on the test set of HumanML3D. So with the text, a person begins to walk up the stairs, this is what we get. So we get some motion which correspond to the input. On top, you can see the score between 0 and 1. And on the bottom, it's actually the text which correspond to the video. This is only as a reference. We actually assume there is no text, and we cannot use the text. So this is the rank at 2, and then the third one. As you can see, all three correspond to the text. Let's see when we train TMR on Kit motion language dataset. So with the text description, a person sits down on a chair and stands up again multiple times. You can see, actually, it's the ground truth. We correctly retrieve the first one. So it does the action, the sitting down multiple times. And if we look at the other examples, it's also doing some sitting motion, or close to it. Let's look at the last example on HumanML3D. With the text, a person winds up his arm and then pitches a ball. As you can see, all the 10 of them correspond to the first 10 of them correspond to the motion. And we successfully retrieving the good one at R10. So to compare with prior work, we can look at the rank at rank 1, which is the accuracy to get it at the first rank. So as you can see, Theos, it's actually Theos used as a retrieval method with the cross-model latent space actually works pretty well, even a bit better than the Guo et al. Prior work. But TMR outperformed both Guo and Theos methods on both datasets, HumanML3D and Kit motion language. If we do some ablation, from the margin loss, if we improve it with the influence, we get a large boost. Actually, influence only and the motion reconstruction loss only are quite similar. But if we add them both together, we get the largest boost. Then filtering negative gives the extra boost we needed. Let's look at the use case of text-to-motion retrieval, which is a zero-shot moment retrieval. When you have a very long sequence and you want to retrieve just a moment when an action appears, such as the backflip, we can use a sliding window approach. When with a sliding window, we'll encode each motion at all the different windows, and then we can plot the similarity metric over time, as you can see on the plot on the right. As you can see on the video and on the plot, TMR picks when the action appears, and we can highlight it in TMR. It can retrieve the moment when the backflip happens. So this is another example with the text pivots body 180 degrees. You can see it picks when the action appears. So to conclude, TMR is a text-to-motion retrieval task. It's not a generative model. And the main recipe is to use the influence loss and the generation losses of TMR. And we can also improve it by filtering the wrong negatives. So TMR can be used for zero-shot moment retrieval, but it can also be used as an evaluation protocol for text-to-motion synthesis. So to summarize, I presented in this presentation actor, Theos, and TMR. So actor for the generation works, actor use a fixed set of action categories. Then in Theos, we use a free-form text input. But then in the other works I didn't present, we use temporal compositions when you have one text at a time with teach. Then we think it's spatial compositionality when you have several texts at the same time. And finally, with the CMC, multi-track timeline control for motion synthesis, it generalizes both the temporal and spatial compositions. So let's talk a bit about the limitation of this work and future work direction. So in all this PhD, we generate the motion in its own without any environment. So it will be very interesting to put human in a context, in a scene, maybe with a real chair instead of the invisible chair, and also with other humans. So it can also, we can think of motion interactions. As you saw, we still have a problem of out-of-description vocabulary. So I think by having more data, this will help a lot in this direction. We didn't focus much also on physical realism. So it can have foot sliding, and the gravity cannot be followed exactly. Also, the motions are not very detailed, so we don't model the face or the hands. For example, the punching motion doesn't close the hands. About diversity, so it's a bit limited still. It corresponds to the diversity of the training data. Because the training data is not very large, we will not get a very large diversity. And also, we assume for this work to have a mean body shape. So if we vary the body shape, maybe we will have more interpenetration. It will not be very adapted. So let's have a look at Sora, which is a work from OpenAI, which is a text-to-video generation. And as you can see in this example, maybe cherry-picked or not, the walking motion seems to work pretty well. So maybe we can try also to go into this direction, in the sense that having training text-to-video motion models, it uses a lot of video data. So we have a lot of video data available online, such as the old YouTube. And so by maybe having a way to extract information from this video, and maybe information from these models, we could try to have this knowledge on all the videos available online and get that to improve our motion generation. But this work are still a bit limited. We cannot really control the generation. And I guess if we ask for more specific motion, I don't think it works super well. So thanks a lot for listening first. Thanks for my advisor. Thanks for all my collaborators and all the people in the lab, which I really enjoy discussing with. Thank you.